Hey, Math 30-2s. Today we're going to look at some applications of exponents and logs, specifically as it refers to finance. So let's talk about simple interest. Simple interest is usually applicable to short-term investments of 1 year or less, or long-term investments where the annual interest is paid to the investor and not invested. So if you invest $500 earning interest at a rate of 6% per year, how much interest would you earn in 1 year? Well, you got $500. And multiply that by the interest as a real number is 0.06. So that should give you $30. How much in half a year then? Will be the same thing. 500 times 0.06, but now it's only for half a year, so you multiply that by a half. So that's going to give you $15. Now roll for 1 month. Well, again, you got $500 at 0.06 or 6% for 1/12 of a year, 1 month, or that's $2.50. All right. If R is the annual rate of interest and P is the initial investment, calculate how much interest will be earned in 1 year. P is the initial investment, and you multiply it by the rate. For half a year, principal times the rate times 1/2 of the year. So principal times the rate times t years. So that's your formula right there. Interest equals principal times rate times time. All right. Where I is the amount of interest earned, P is the principal or the initial investment, R represents the annual rate of interest, expressed as a real number, which is a decimal, and T represents the time in years for which the money is invested. So example 1, Millie invests $2,350 at 7% per year for 6 months. Calculate after 6 months her simple interest earned on Millie's investment. So interest would be the principal, $2,350, times the rate, 0.07, times the time, 6 months, which you could say 6 out of 12, or half a year if you wanted. Do that calculation. You find out that's $82.25. What's the value of her investments then? Well, the value is going to be the principal plus the interest. So the principal was $2,350. The interest was $82.25. So her total value right now should give her $2,432.25. All right. Compound interest. Let's look at that. Well, simple interest is the principal at the beginning of the second year is the same as the principal at the beginning of the first year. So, same principle. In compound interest, the interest earned during the first year is added to the original principal, and that forms the new principal the next year. So to understand this comparison, let's look at the next couple of pages. So a bank offers 2 types of savings bonds: regular, which pays simple interest of 9% per year, and compound, which pays 9% per year, but now it's compounded annually. Consider initial investment of $15,000 in each bond. Simple interest. The simple interest each year is 9% of 15,000, so you go 0.09 times 15,000. That gives us $1,350. Complete the table. So every year we add $1,350 to the preceding one. So in year 6, $21,750 plus $1,350 gives us $23,100. And add another $1,350 and we get $24,450. Add another $1,350, we get $25,800 after 8 years. Well, how's that compare to compound interest? Complete the following to determine the compound interest and the value of the bond. So in year 1, the value of the bond is the principal plus the interest. So we start with the principal of $15,000, and we learned how to find the interest, 15,000 times the rate, 0.09. Well, if I factor out 15,000 divided by 15,000 is 1, and 15,000 times 0.09 divided by 15,000 is 0.09. So if I add 1 plus 0.09, I come up with this value. And if you do that on your calculator, That turns out to give us the amount after year one, 16,350. That's great. Now in simple interest, we just added another 1350 to that. With compound interest, this becomes our new principal. So 16,350 goes where the principal is, or 15,000 times 1.09. That's the same as 16,350. To that, we have to add the interest on that. So 15,000 times 1.09 is what we started with, and then we multiply that by 0.09 to get our interest. Now I've got an algebraic expression. Let's factor out 15,000 times 1.09. So 15,000 times 1.09 divided by 15,000 times 1.09 is 1. And over here, 15,000 times 1.09 times 0.09 divided by 15,000 times 1.09 is just 0.09. So you add those together, you get two 1.09s. So that's the same as saying squared. That's the value after year two. Definitely not the same as simple interest. This now becomes our principal in year three, and to that we have to add our interest, which is our principal times 0.09. So again, you factor out the 15,000 times 1.09 squared, we come up with this statement, which if I simplify is 15,000 times 1.09 squared times another 1.09, or 15,000 times 1.09 cubed. All right. So the value of the bond at the end of each year is 1.09 times the value at the end of the previous year. So we can see what's happening. 15,000 times 1.09 now to the fourth, and 15,000 times 1.09 now to the fifth, and we continue that pattern until we get 15,000 times 1.09 to the exponent n. All right. The values, if you use your calculators and keep going with these values, we get 21,173.72, and then we get 23,079.36, and we keep going until eventually we get down to the last year's 29,888.44. All right. So the value at the end of the n years is this formula. All right. Plot the data from the simple interest and compound interest tables. Do not join the points. So you go ahead and do that. See if you come up with the same thing I come up with. So when I plotted this, I used blue for the simple interest and I used green for the compound interest. And we can see that the graph shows that the simple interest is growing in a linear pattern and the compound interest is growing in a exponential form, which is much quicker. So the final amount A can be written as an exponential function of the form A equals A times B to the exponent n, where n is the number of years. State the values of A and B and write the function in this form. So the initial amount for compound interest was $15,000. The B value, the base of the exponent, is 1.09. So if I write it in that form, amount equals $15,000 times 1.09 to the exponent n. How do the values A and B relate to the scenario in this question? Well, A is the initial investment, or the principal. And B is the annual interest rate expressed as a decimal added to 1. Interest rate expressed as a real number and then added to 1. Let's see what happens on the next page. Well, the difference between the exponential growth and the linear growth is more apparent if we extend the graph in f to more than 20 years. So this would be our compound interest, and this would be our simple interest. So use the compound interest graph to estimate the number of years and it would take for the initial investment of $15,000 to increase in value to $50,000. So it started at 15 and we now want it to get to 50 using the compound interest graph. So here's 50,000 on the compound interest graph where it intersects, and that would be at 14 years. So 14 years we should write in here. And $100,000 on the compound interest graph. Here's $100,000. It intersects right here. So if I go down from that point, $100,000 looks like it's about year 22. All right. So it would take 22 years to get to that amount of money. $100,000. It says an algebraic solution will be developed later in this lesson. Consider an investment of $30,000 compounded annually at 5% per annum. Write an exponential function which will represent the final amount after n years. So the final amount would be the initial amount, 30,000, times 1 plus our interest rate as a real number, 0.05 to the exponent n. Consider investment of $750 compounded annually at 3.5%. Write that exponential function. So the amount would be an initial investment of $750. 1 plus that interest rate is a real number, 0.035 to the exponent n. In general, A, the final amount, or the value of the bond, P is the principal of the initial investment, I is the annual interest rate as a real number, and n is the number of years. We have the following formula. P times 1 plus I to the exponent n. So if we look at compound interest, where we're only going to look at compounding annually. That's step one. We're just compounding annually. All right. So we're just going to deal with compounding annually here. It says the formula which can be used to express this, we just developed. Here are the parameters. A is the final amount, P is the initial investment or the principal, I is the annual interest rate as a real number, and N is the number of years. So let's do an example. Travis borrows $2,000 from his parents and agrees to pay off the loan in one payment. When he graduates, interest is charged at 3.5%, compounded annually. How much does he owe at the end of the second year? Well, we've got our formula. What's his amount that he owes? Well, he borrowed $2,000, so that's his principal, at a rate of 3.5%, so 1 plus 0.035. So this is to the exponent 2. All right. So 1.035 to the exponent 2 because we're paying it off after 2 years, it says. Second year. There we go. So find out that amount. So the amount would equal $2,142.25. If he paid the loan off after 2 years, how much interest has he paid? Well, the interest would be the original amount, or the final amount, sorry, $2,142.25. Subtract his principal, which was $2,000. So he's paid $142.25 in interest. Travis was unable to pay the loan off after 2 years. When he eventually did pay the loan off, he paid an extra interest amount, total interest amount of $458. Write an exponential equation whose solution gives this the time period for this loan. So we now know the final amount was $2,000 plus an interest of $458. The initial amount was $2,000. We know that it was at 0.035%, but we're not sure how long it was for. So now we have to solve for n. Solve this equation algebraically. So step 1, divide both sides by 2,000. So you get 2,458 divided by 2,000 equals 1.035 to the exponent n. Now you can do a couple things here. We just looked at taking the common log of both sides. So if I do that, common log of 2458 divided by 2,000 will equal the common log of 1.035 times to the exponent n, or I'm bringing my n out in front, and that's a common log of 1.035. And now to solve for n, we can divide both sides by the common log of 1.035. So I've got the log of 2458 divided by 2,000 all over the common log of 1.035. If you do that, you get n is like 5.999, so we will say, and so on. So we would say 6 years to pay off the loan. All right. Compound interest formula on the previous page was adapted for cases where the compounding does not occur annually. Example, semi-annually is twice a year, quarterly is 4 times a year, monthly is 12 times a year. The formula is the same, but I and n are slightly different depending on the compounding periods. So A is still the final amount and P is still the principal, but a huge difference for I and n when it's not compounded annually, if it's compounded more than annually, or less, or different than annually. So I represents the interest rate per compounding period, and n represents the number of compounding periods. All right. Note that I does not always represent the annual interest rate. I is calculated as the annual interest rate divided by the number of compounding periods per year. Put a big star beside that. Common error people make. And n does not always represent the number of years, but it's the number of years times the number of compounding periods per year. All right, so those are two common errors. I and n now change. So example 3. If the annual rate of interest is 6% per year, state the interest rate per compounding period and the total number of compounding periods in each case. So if it's compounded semi-annually for 5 years, I should be the interest rate, which is 6%, twice a year, so we have to divide that by 2. So it becomes 3%, or as a real number, 0.03. And n, number of compounding periods, well, we're doing this for 5 years, twice a year. 5 years, twice a year, there are going to be 10 compounding periods. All right. So you can see that I and n change depending on how many times we compound it. If it's compounded monthly for 6 years, well, I has an interest rate of 6%, but it's compounded monthly, so I have to divide that by 12. So we get 0.5%. Or as a real number, that's 0.005. And n is compounded for 6 years monthly. So there are 72 compounding periods in that situation. Example 4. Let's say $1,000 invested for 5 years. $1,000 for 5 years, 6%. Complete the table to calculate the final value of the investment if the interest is compounded according to the period of time given in the table. So, number of compounding periods per year, if it's annually, that's once. Semi-annually, there are 2 compounding periods per year. Quarterly, 4 times a year, and monthly, it's compounded 12 times per year. Total number of compounding periods, this will be our n. All right, so we're doing it for 5 years. 5 years, once a year, 5 compounding periods. 5 years, twice a year, 10 compounding periods. 5 years, 4 times a year, there are 20 compounding periods. 5 years, 12 times a year, we have 60 compounding periods. interest rate per compounding period. So this is going to be our I. So let's write this as a real number. All right, 6% once a year, 0.06. All right. Semi-annually, so you have to go 0.06 divided by 2, which is 0.03. Quarterly, our interest divided by 4 times a year. So that gives us 0.015. And then 0.06 divided by the number of compounding periods per year, which is 12. That gives us 0.005. All right, so our formula, A would equal our initial investment of $1,000 times 1 plus our interest, 0.06, to the exponent n 5 times a year. All right. Semi-annually, 1,000. 1 plus our interest now is 0.03. 0.06 divided by 2, 0.03. Compounded 5 years, twice a year, 10 compounding periods. Part C, quarterly, 1,000 times 1 plus 0.06 divided by 4 is 0.015, and it's 5 years, 4 times a year, 20 compounding periods. And finally, 1,000 times 1 plus 0.06 divided by 12 is 0.005, and 12 times a year for 5 years is 60 compounding periods. So if it's compounded annually, we do this calculation right here, and we come up with a value of $1,338.23. By changing the word from annually to semi-annually, we now increase the number of compounding periods to 10, but decrease how much our I is each period. But we end up with more money, $1,343.92. Compounding it quarterly, we get another value of $1346.86. And compounding it monthly, we come up with $1348.85. So for the same amount of money over 5 years at the same rate of interest, just by changing it from annually to semi-annually to quarterly to monthly, how much we compound it, we end up making more money every time. All right, just by changing a simple word. Let's look at example 5. Christine invested $2,500 for 4 years, compounded semi-annually, and received $843.26 interest. What was the annual rate of interest? Well, let's write down the things we know. We know the final amount, $2,500. Plus she received $843.26 in interest. So that final amount should be $3,343.26. We know what our principal was. That was $2,500. We're not sure what the interest rate was. That's what they're asking us. What's the annual rate of interest? So we have to figure out what I is. But we know it was compounded for 4 years semi-annually. So 4 years, twice a year, we know there's 8 compounding periods. 4 times 2. All right, so let's substitute into our formula. Our final amount is $3343.26. That equals our principal, $2,500, times 1 plus I to the exponent n. Well, we know n is 8. So let's solve for I. Divide both sides by 2,500. 3343.26 divided by 2,500 will give us 1 plus I to the exponent 8. Now how do I get rid of that exponent 8? Well, we've talked about how to do that already. We take both sides to the exponent 1/8. Right, do the same thing to both sides of this equation, and that will eliminate that exponent of 8 on the right hand side. So now I just have 1 plus I. And if we do that calculation on the left hand side, we get 1.037. So if I now minus 1 from both sides, I find out that I equals 0.037, or I is 3.7%. But we know it's compounded semi-annually. All right, so the interest rate, the annual interest rate, should be 2 times I. So the annual interest rate will be 2 times 3.7%. So that'd be 7.4% as an annual interest rate. Excellent. Let's do example 6. Andrea borrows $7,500 from her parents to buy a new car. Her parents charge her interest at a rate of 4% per annum, compounded quarterly. When she pays off the loan, she has to pay $785 in interest. What was the length of her loan? So now the amount is $7,500 plus $785, so it's $8,285, right? She borrows that and she paid that much in interest, so the amount is the sum of those two values. The principal is $7,500. The annual interest rate is 4%. 4% compounded quarterly. So we take 0.04 and divide that by 4. That's our I value, 0.01. All right. And N, we're not sure what the value of N is, and that's what we're asked to find. What's the length of our loan? All right, so let's use our formula. Final amount, 8285, equals our principal, 7,500, times 1 plus I, which is 0.01, to the exponent N. So we're going to divide both sides by 7,500. So we get 8285 divided by 7,500 equals 1.01 to the exponent N. Now we said earlier if I take the common log of both sides, this will work. 8285 divided by 7,500 equals the common log of 1.01 to the exponent N, written as N times the common log of 1.01. I now divide both sides by the common log of 1.01, and I find out what N is. So the log of 8285 divided by 7,500 all over the common log of 1.01 will give us our N value. And you work that out and you get N equals 10. But remember, N is not the length of the loan. N is the number of compounding periods. So this should have been number of years times 4 if it's compounded quarterly. So that means we have to take 10 should equal number of years times 4. So I now have to divide both sides by 4. So 10 divided by 4 is 2.5, or 2.5, will equal the number of years of the length of the loan. All right? Great. You guys have your assignment? Let's get after it.